Now we're going to do the error analysis for Simpson's method. So we're working with our function we've been doing on the interval, and here is the answer for the integral. First thing you notice is that even for just 5 subintervals right here, Simpson already is very close to the answer, because here is 6.437, almost 6.44, and here you have those digits already there. So this is a very good method. In fact, when you finally get to 5,000, and those other methods were struggling to get toward the final answer, Simpson's pretty much there. Just this last digit right here is different than this one. So it's very good. Now let's analyze the error. When you increase by a factor of 10, let's see what happens. This first error was about 0.003 right here, 0.003, rounds off. And now when you increase by a factor of 10, that was 0.003, now it's 0.000003. So we've divided by 10,000. So the error went down by a factor of 10,000 when we just increased the n a factor of 10. That's a huge improvement. So then going from 50 to 500, another factor of 10, the error did have 1, 2, 3, 4, 5, 6 zeros before it got to a number. Now it's at 10 to the negative 11th. So that would be 11 places here. So to get an idea of this increase or decrease in the error coming from here, if we express this first number here in scientific, it would be 3.39 something times 10 to the 1, 2, 3, 4, 5, 6, 7, negative 7 power. So you can see that we've jumped to a number in scientific notation that has 10 to the negative 11th. So we've gained 4 decimal places again. So that's a 10,000 factor decrease in the error. Then when you go finally from 500 to 5,000, an increase of 10, factor of 10 of n, the error, you can see, goes from 10 to negative 11 to 10 to negative 14, again dividing by 10,000 to get to the next one. So your error has decreased by a factor of 10,000. And of course 10 to the 4th is 10,000. So that leads us to this final conclusion. As n increases by a factor of 10, the error decreases by a factor of 10,000. So we get a resulting increase in accuracy that is the 4th power of the processing work we put in. That's a great method. So let's recap the methods that we've seen. First, the left and the right. They are both first power methods, meaning that an increase of n by a factor of k, we were using 10, but it could have easily been 5 or 6, a factor of 6, anything, factor of 20, results in a decrease in the error by a factor of k to the first. So it's basically an even trade-off. Put 10 factor in, get a 10 factor decrease out. The trap in the mid point methods were better. They were second power methods, meaning that an increase of n by a factor of k results in a decrease in the error by a factor of k squared. So we saw that when we increased the n size by 10, the error went down by a factor of 100, which is 10 squared. And again, we use 10 so we can easily see the decimal places move, but that k factor could have been anything. Then Simpson came in, and it turned out to be a fourth power method, meaning that an increase of n by a factor of k results in a decrease in the error by a factor of k the fourth. So if you increase n by a factor of 10, the error is going to go down by a factor of 10,000. So every time you increase by a factor of 10 in your n, your error divides by 10,000 to get to the next error value. So Simpson is the best of these methods that we've seen. But there are other methods and improvement on even that, but that's not in the scope of the course. Lucky for you.